Hello class. I'm trying the live stream again to see how well it works. I'm using my own data though, so we'll see how long it takes to upload. I have not had success in uploading yesterday's lecture. I'll be trying it again soon. So you're missing a lecture, but I have it in my phone. I just haven't been able to get onto the internet. So today's lecture is the second lecture that I'm giving uh, with the um, with the subject of chemical kinetics. Oh, hi. There's somebody already online. Good. Hope it's a student. Marvin. Hey, Marvin. So I'm on page 587 right now, but this is the homework I gave yesterday. I gave page 585 from the chapter, and this is, I'll read the question for you. So it says, what is the reaction order of the reactant H2 in equation 1411? B, what are the units of the rate constant for equation 1411? And equation 1411 is hydrogen gas reacting with iodine gas to give you hydroiodic acid in the gaseous form. So here it is. This is the reaction. The rate equation would be that. Actually, it's asking what is the reaction order of the reactant H2? Well, it's first order, and so is I. They're both first order because they give you the reactants. They give you the rate law right after the equation. If you look at 1411 on the top of page 584, it says rate equals K, that's the rate constant for that particular reaction, times H2 concentration times I2 concentration. Neither one of those concentrations is elevated to any power, so it's the power of 1. And that is the rate law then. And it asks what is the reaction order of the reactant H2 in equation 1411. For some reason I put I2. It's first order in H2, but you could say and I2. Both of them are first order from the rate law that they give. Then if you want to find the units of the rate constant, what you do is you divide both sides by H2 and I2 so that you isolate K. That's what I did here. So the rate divided by H concentration divided by I2 concentration equals K. The units of the rate are molarities per second. The units of the hydrogen concentration and the iodine concentration are molarity. Two of them cancel so that you're left with per second over molarity, which basically is per molarity per second. You can also write it this way if you like. Either one of these two formats is correct. Molarities to the -1 is like putting it in the denominator. The next practice example I'd like to illustrate is how you can use initial rates to determine rate laws, like I said last lecture. It says the rate law for any chemical reaction must be determined experimentally. It cannot be predicted by merely looking at the chemical equation. We often determine the rate law for a reaction by the same method as we apply to the data in table 14.2. So let's look at a sample exercise. Hi, Tambe. So in practice example on page 587, it shows the following data were measured for the reaction of nitric oxide with oxygen. It shows you 2 nitrogen oxide gas plus 2 hydrogen gas gives you nitrogen gas plus 2 water. And there's 3 experiments that they did where they varied concentrations of either the nitrogen oxide or the hydrogen. And then they observed the effect it had on the rate. So they performed 3 experiments. The key here is to look at an experiment where one of the reagents is not changed and the other one is. That way you can, if there is any change in the overall rate, you can attribute it directly to the fact that that substance was changed in concentration. So this is in the middle of page 587. What I did, well, I'm going to write down the answers that I got, because if I just talk it through, you might not pick up what's going on. The trials look like this. So you had 3 experiments, 1, 2, 3. You had NO concentration and H2 concentration. What else was there? And the initial rate in the molarity per second. And the NO concentrations were 0.1, 0.1, 0.2. And the hydrogen concentrations were 0.1, 0.2, 0.1. And then you had 1.23, 2.46, and 4.92 times 10 to the negative 2 each time molarities per second. Okay, so those are your experimental parameters. The key here is to interpret what the data is telling you. So if you look at experiment 1 and 2, they've maintained the nitrogen monoxide concentration constant, but they've doubled the hydrogen concentration, so that causes a doubling of the rate. If there's any change in rate, it's entirely attributable to the fact that there's a doubling of the hydrogen concentration, because this can't be having an effect. It's the same before and after. So the initial rate doubled when they doubled the concentration of hydrogen. Now let's see the effect it has when you double the NO concentration while keeping the hydrogen concentration constant. So in this in experiments 1 and 3, the concentration of hydrogen is kept at 0.1, but the concentration of NO is doubled. What effect does it have on the rate? It quadruples it, because 1.23 times 4 gives you 4.8 plus 12, 4.9, it gives you 4.92. So it quadruples the rate. So let me write that down for you. In experiment 1 and 2, the NO concentration is constant. Therefore, any rate changes are caused by H2 concentration change. A doubling of H2 concentration causes a doubling of rate. The reaction is first order. With respect to hydrogen concentration. Looking at 1 and 3, the hydrogen concentration is kept constant. But NO concentration is doubled. Which quadruples the rate. So it's second order. This means the reaction is second order with respect to write the rate law. Rate. Let's erase this top part so we don't confuse you. the rate is equal to K, the rate constant, times the concentration of NO times the concentration of H2 to the power of 1. That would be the rate law for part A. Then in part B, it asks you to find the units of the rate constant, if I'm not mistaken. It says part B, calculate the rate constant. Okay, if we have to find rate constant itself. So K is equal to NO concentration squared times H2 over the rate. And the units of oops, no, I wrote it upside down. These go under there. Yeah, it goes rate over NO concentration squared times H2. Okay, that's better. The rate, excuse me, is molarity per second. The units here are molarity squared, and the units here are molarity. And you could eliminate that. And you get 1 over molarity squared times seconds, or you could say molarities to the -2 times seconds to the -1. Those are the units of K. But we still don't know what K are. These are the units. Now let's pick a set of data and plug it in and see what we get for the actual value of K. Just pick any one of the experiments. I think I picked experiment number 1, 1.23. That's right, experiment number 1 data. So I plugged in the numbers. And it says K equals 1.23 times 10 to the -3 times 0.1 squared times 0.1 gives you 1.23 times 10 to the -3 over 0.001 and 10 to the 0. Or how many sig figs are you allowed? You're only allowed 2 sig figs, so you have to report 1.2. And the units is molarities to the -2 times seconds to the -1. That would be your answer for this question. And in part C, it says, calculate the rate when the nitrogen monoxide concentration is equal to 0.05 molar and the H2 concentration is equal to 0.15 molar. So let's do that as well. If NO concentration equals 0.050 molar and H2 concentration equals 0.1, then rate, which we were given, the rate law, we figured out is this. Now if we just plug in the numbers, 1.23 molarity to the -2, second to the -1 times 0.050 molar times 0.150 molar. Don't forget to square that part. And you will get 4.6125 in your calculator. It says it was unable to reconnect. I'm hoping you got something. I hope it kept on recording. In the meantime, I'll keep teaching. The next part is dealing with first order reactions. First order reaction is one whose rate depends on the concentration of a single reactant raised to the first power. For a reaction of the type A goes to products, the rate law may be first order. So rate is equal to negative delta A concentration over delta T, and it equals K times A concentration. Now you can give different forms of the rate law. You can integrate it to give a graphable form, The form of the rate law which expresses how rate depends on concentration is called the differential rate law. Using an operation from calculus called integration, this relationship can be transformed into an equation that relates the concentration of A at the start of the reaction, A naught, to its concentration at any other time, AT. Let me summarize that for you. This is on page 587 of your textbook, Brown and others. I have to go to Montreal tonight to take care of some business, so I'll try to upload the first lecture so you can catch up. In the meantime, make sure you start reading chapter 14. So in first order reactions, and also in the meantime, you can watch my playlist. I have a kinetics playlist. Watch it. It was recorded 8 years ago, and it's online. That one you can access. And it's not even me lecturing, it's my student teacher lecturing. She's now a teacher in the Toronto Catholic District School Board, so the subject is the same. The face is prettier. Right is equal to negative delta A concentration over delta T, and it equals K times A. And if you integrate it, what you get is ln of A sub T minus ln of A naught equals negative KT. And you can rearrange that to ln of A sub T is equal to negative KT plus ln of A naught, which looks like a y is equal to mx plus b form. And you can also say A is equal to A naught, where A naught is the concentration at the beginning of the reaction, e to the power of KT. If K is positive, you're going to have exponential growth. If K is negative, then you're going to have exponential decay. I'll do one example of how that works. And this is from the practice example on page 588. Where they have dimethyl ether is turned into methane, hydrogen gas, and carbon monoxide gas. Let me read the question to you. 588. The decomposition of dimethyl ether at 510 degrees Celsius is a first order process with a rate constant of 6.8 times 10 to the negative 4 seconds to the minus 1. If the initial pressure of dimethyl ether is 135 torr, what is its partial pressure after 1420 seconds? So we're told that K equals 6.8 times 10 to the negative 4 seconds to the minus 1. We're told A naught, the initial concentration, is 135 torr. A is what we're looking for, and T is 1,420 seconds. So we're going to use A is equal to A naught e to the KT as our first order decay. The A naught is 135. E is in our calculator, so we're not going to write it down, but it's 2.71 roughly. The value of K is negative 6.8 times 10 to the negative 4 because it's a decay. All right, it's decaying. There's a decrease. So the value of K can be increase or decrease. In this case, you have to put it negative to have it decrease. If you put a positive value, the number is going to go up, and you're going to get the wrong answer. You just have to recognize that it's a decay. And that 1,420 seconds elapse. So you see seconds to the minus 1 and seconds will cancel, and it'll leave a pressure in torque. So A is equal to 135 times e to the power of negative 0.965, 9656. And that equals 135 times 0.3807, 546, 78. Continue the calculation up here. You get that A is equal to 51.401, 8816 torr in your calculator readout. Of course, you're going to report it to 2 sig figs, so you're going to say 51 torr. I'm going to give you how to deal with first order plots, and I'll just give you some short homework. When you do first order plots, because a lot of times you'll get data, and the best way to represent your data so that you include all the points to graph all the data. But very often when you do experiments, you're going to get some deviations from what you expect. That doesn't mean you did your experiment wrong, it's just the way things go. Sometimes you measure one thing a little more, you measure another thing a little less, so your points will deviate slightly from the curve. But if you take enough points, the errors tend to average out because errors are random, whereas experimental results tend to all move in the same direction. So because errors tend to cancel out, especially if you have multiple points, taking multiple data points helps to increase the confidence of the data that you collect. So for a first order plot, meaning it obeys first order decay or growth, you're going to plot ln of A at certain time t equals negative kt plus ln of A at time 0. So this is equivalent to y, this is equivalent to the mx part, and this is the plus b part of a straight line plot, right? This is the slope, that's the x value, that's the y value, and this is the y-intercept. So if you plot ln of A at some time t versus time, you're going to get a line that's going to be straight. The slope is going to be delta y over delta x, which equals m and is equivalent to negative k. And this will be the ln of A naught. The intercept will be ln of A naught, the time 0 value of A. So, if, nota bene, NB, if a plot of ln of A versus A sub t versus time yields a straight line, the reaction is first order with respect to concentration of A. I'm gonna stop there, but try this. I'll give you a first order type problem. If I can find one. Bear with me. Okay, try 1433. 1433 for homework. Homework number 1433. Okay, and I'll see you tomorrow.